came together where we said, well, now not only can we find what a common charge is for a given element, what its most common charge is going to be, but we can also put them together to form these compounds in a particular way. And now we're going to look at the last piece of that, which is how do we actually give these names? And if we have the names, how do we write the formulas from the names? And we're going to go through a couple rules of how to do this. Now, for the most part, we've already kind of used these rules, so they shouldn't seem way out there. But we are going to look at one other category of metals, kind of these ones in the middle that we've been ignoring, and talk about how naming those is going to be a little bit different from what we've been doing. All right, so let's start this off here. Naming ionic compounds. So compounds made from more than one ion. How do we give them names? One thing that might be helpful is just to look at one that we know. NaCl. We've talked about this a bunch this year so far, and you've probably seen it in the past. What's the name of that?
Sodium chloride.
Sodium chloride. So if you assume that that is representative of all ionic compounds, which it kind of is, what rules are you using to go from the names of the elements to go to that name? In other words, what's changing or not changing? We have Na, which we look up on the, well, there's no words up there, but if you looked at a periodic table with words, you'd say that under Na it said sodium. You'd say that under Cl it said chlorine. So what has changed when we put those together and come up with this name of sodium chloride? First, just something as simple as the order. What can we say in general about the order of ionic compounds? Let's look at another example. This one we just looked at last time. So MgS is magnesium sulfide. NaCl is sodium chloride. What do those names have in common? You don't have to think too hard about this. Just like what's...
From the same?
Yeah, the what?
From the same groups?
So like how are the metals named in each of those? Is there any change from what you might find on the periodic table for the name? There's not, right? Sodium stays sodium, magnesium stays magnesium. So that's actually our first rule. Is when we name ionic compounds, the metal name doesn't change. And a second rule is with the order, is going to be metal first, and then non-metal. Even if it's not written that way, that's the convention for the name. So we could, instead of writing NaCl, we could write ClNa. Not usually how it's done, but nothing wrong with that. It's two elements put together. We would still call that sodium chloride because we would still name the metal first. So the metal always goes first. So our first two rules of naming these are probably already somewhere in your head, that the metal name stays the same, sodium or magnesium, and the order makes the metal first and the non-metal second. So what do you think is the third rule? What does change going between the element names and the compound names? The what?
The end.
The end. How does the end change? Yes. How does it change? Let's look at these two names again. What does S, what does it say under S if you look it up on the periodic table? It says sulfur. But what's the name when S is in a compound? Sulfide. What does Cl say on the periodic table? And what does it say in the compound? So what might you say is a rule for what you do to the anion, the negatively charged ion? Yeah. Yes, you're all correct. So our final rule for this then is drop the end off the nonmetal and add ide. Now, drop the end off is a little bit trickier than it sounds because it's different for different elements. So chlorine, you lose the INE and you add the IDE. So you lose ene and you add ide. But sulfur, you lose the and you add ide. Carbon, you lose the on and you add ide and get carbide. So there's a little bit of how exactly do we do this? And the way to get that is just through practice. So when you go through and do all these problems where you're asked to name things over and over again, and then you check, you realize, oh, okay, well, I thought that phosphorus would be phosphoride, but actually it's phosphide. And to me, when I'm grading these things, it's not a big deal. If you write phosphoride instead of phosphide, I don't really see that as a problem. But when you are trying to communicate more broadly in chemistry, you might raise some eyebrows if you misspeak those. So in the context of this class, I'm not that worried about it, but it's probably worth it to learn how to say that correctly. Part of this is just experience too. As you use more and more common ions, and as we do problems with them and we work with them in lab, it's going to sound weird to you to use the wrong one. So the right one is just going to sound better. All right. So that's our rules. There's actually a fourth rule that we're going to get to in a minute. But let's do some practice with just these, and then we'll go back and add them. I'm going to put up some compounds, and you're going to name them. And then I'm going to list a couple words, and I want you to write the formulas for them. We're going to talk about how we do that. All right. Oh, I guess I did a word first. You don't have to do this in this order. If you have a little periodic table with you, either in the book or in your lab notebook, or if you have a pocket telephone and you can pull up something on the internet, that might be helpful here, just so you have the names for the ones that you don't know. These three examples all follow the rules that we just talked about. I want you to take your best shot at it and try to either name or draw a formula for each of those. They're not all easy, for sure, but give it your best shot. I'm just pulling up the book here. All right, who feels good about one of these? What you got for one of these? Any of them? Yeah.
First one, LiO.
Okay. LiO.
Yep.
All right, others? Is that what you got? Do you get anything different? The second one? What'd you get? Oh, strontium bromide. Okay.
How we have to mention this too?
What?
How we have to mention? Do we have to mention this too?
No, we don't. And the reason why, we're going to go back to this first one because that LiO is actually not right. There's one issue with it. Yeah.
Two Li's, right?
Why do you need two Li's? That's correct, but
Because the line has one, it has an A1 group.
yeah.
What? What happened?
Sorry. Sorry, you're almost right, but there's a little 2 there that goes next to the Li.
Why is that now?
Yeah, why is that? Let's talk about that. Same question that just came up from the strontium too. How does the name tell us how many of each ion there is? And the answer is it doesn't. But for these types of compounds, the charges are known. Remember last time we talked about how we can determine the charges of ions? We need to know those to be able to do this conversion back and forth between the names. Now, you don't have to memorize every charge of every ion. Remember, we talked about well, first of all, we talked about how you can build it to figure it out. So you can build these little buckets, right? And you can figure out how many electrons are likely to be lost or gained to fill a bucket. But the periodic table actually will help us with that too. So let me pull this picture up from your book. This is page 175. There's our periodic table, but in many of our groups, we can determine the charge based on these buckets. And so if you look at, for instance, this group 1A, all of those have a common ion of +1. So that's their ion, a +1 ion. And why is that? Because all of those have one extra electron in that valence bucket, the valence shell, and they want to lose that one electron to get to the full shells. So all of them in that category are going to generally make +1 ions. All of them, all the ones next door, with the exception of the top, because that one's a little weird, but that's fine, make +2 ions. Same reason, lose 2 electrons. We're going to ignore this middle stuff for now and jump over to the other side. The nonmetals go the other way. Remember, we looked at filling buckets, or you may have looked at this in the homework for things like fluorine and chlorine, and you'll find that if you count up the electrons in those, there are 7 in that last bucket, 7 in that valence shell. And so they want 1 more to get to 8. And getting 1 more electron means you're at -1 ion. So in order to write the names, or write the formulas from the names, you need to know the charges of the ions. And in a minute, we're going to talk about what happens with these middle ones where you don't necessarily know the charges. But for now, the ones where we do know the charges, the ones to the far left and the ones to the far right, we can do this. So that first one, lithium oxide, here's how you find the formula from that name. You don't just write down LiO, because lithium is Li and oxide is O. What you want to do is write down the individual ions and figure out how many of each you need to make a balanced compound. So when I saw, so let's try it with this next one, potassium selenide. If I'm going to try to find a name for this, I first want to write down each individual ion. So what is a potassium ion? K, and what's its charge? +1. So we want to have that on there, that the common ion of potassium is +1, which we know because it's in group 1A. Selenide, what element does that come from? Do you think, if you were to guess? Selenium, which is Se. Now that one's not on our little chart from the book, but what do you think its ion would be if you had to take a guess? 2 minus, because it's in that same group with oxygen and sulfur, which are also 2 minus. And so we know that this one's probably going to be 2 minus. All right, so we have a +1 potassium and a -2 selenium, selenide. How do we balance that out in a compound so that it's 0 overall? Right, we need 2 of these potassiums for every 1 Se. You see that, how that works? So 2 of the pluses for every 1 of the 2 minuses gives us 0 overall. So the formula for potassium selenide is K2Se. Because we have to make sure that those overall charges balance out to 0. So that makes our life a little bit harder when we're going from a name to a formula, but it makes our life a little bit easier when we're trying to use a name because we don't have to worry about all that. So that third one, Al2N3, how do we name that? Aluminum nitride, right. Aluminum nitride. Notice that element and compound names are not proper nouns, so they don't get capitalized unless they're at the beginning of a sentence. All right, let's try one more, and then we'll go to the other type. So write a formula for magnesium iodide. Make sure you are looking at these names carefully too. There are several elements that have very similar names. And you get to use a periodic table with the names on it. So please use that if you need it. In this example, people often mix up magnesium and manganese, which are kind of similar sounding words. So make sure you're really looking up magnesium and not manganese, which is Mn. So you got a formula for magnesium iodide? What'd you get? Mgi2, good. So you found that the Mg is 2 plus, and the iodide is -1, so we need 2 of them, and that makes overall Mgi2. Great. All right, now let's get tricky. That's too easy, right? We're gonna make it a little harder than that. No, there's one more. That fourth rule deals with what happens when we have these weird things in the middle. And the book labels a few of them. We're actually going to look at a lot more. We're gonna use all of them. I don't know why they only have a few listed in their table there. But what do we do when a metal has an unknown charge? So all of these metals in the middle can form multiple different types of ions. And we need to specify which type they're forming. So let's take iron, for instance. Iron is Fe. We could write 2 formulas, FeCl2 and FeCl3. Those both exist. And if we were to name those, we would call them both iron chloride. So clearly that name isn't good enough because that name doesn't discriminate between those 2 species. If we just say iron chloride, we don't know if we're talking about FeCl2 or FeCl3. So if somebody said, hey, give me a formula for iron chloride, how would you know which one to write down? You wouldn't. So we need a way to talk about compounds where the metal can have more than one possible charge. And the way we do that, at our fourth rule here, if the metal can have more than one possible charge, show that charge Okay. We show that charge as a Roman numeral in parentheses. So like 1, 2, 3, 4, etc. Right after the name of the metal. So keeping that rule in mind, let's look back at our two examples down here, FeCl2 and FeCl3. What is the charge on the metal, on Fe, in FeCl2? How could you figure that out? So what is the charge on Fe? +2, how'd you know that?
Because you need 2 electrons to even it out.
Yeah, we know that Cl is one of those ones that never changes. It's always -1. So if we've got 2 Cls, that's a -2 overall. We need a +2 on the iron to balance it out. So that has to be +2. So what does the charge have to be on this iron over here on the right? +3, same reason, right? And that's how we're going to separate these two names. So we're going to call this one iron 2 chloride. And we're going to call this one iron 3 chloride. The most common mistake here is forgetting that those Roman numerals in parentheses indicate a charge. It's not the number of atoms. A lot of people, when I look at these on quizzes and things like that, in exams, a lot of people want to say, oh, iron 2 chloride, that means Fe2Cl. That's not true. That number in parentheses is the charge on the ion, not the number of them that are in the compound. So try to keep that in mind, and practice will help with that as well. So let's do some practice of these of this type. So try these 3. You've got a couple that they're actually all oxides in this case. So a couple that you're going to name and one that you're going to write the formula of. See what you get. You try that. All right, who wants to give these a shot? Which one do you like? Yeah.
The first one is it's copper, right?
Yep. Yep. Do we have to put anything in parentheses? We do. So here's another question about this. How do we know whether or not we need something in parentheses? What's the rule for that?
Parentheses go in the middle? Right there?
Yeah, right after the name of the ion, the name of the metal. Right. We need those parentheses when there are multiple possible ions for a given element. Note what we wrote up here. If the metal can have more than one possible charge, show the charge. How do you know if a metal can have more than one possible charge or not? Yeah, where it is on the periodic table is going to tell us. So look at those first two columns. No variation there, right? So if it's one of these ones in the middle, you can be pretty sure that it's going to need those parentheses. Now, there's a couple weird exceptions, and you don't need to know these, but aluminum, zinc, and silver actually only have one possible charge, even though they're kind of in that middle range. But we'll just say anything in this middle range, you need to do that. So when you look up Cu and you see that's copper, and you see where it is on the periodic table, kind of in that middle range, what we call the transition metals, that tells you, oh, this is one of those ones that could have more than one charge, so we have to specify its charge in parentheses. So what number goes in the parentheses for this compound? 1 or 2? Got some 1s, got some 2s. Well, what's the charge on copper, on each copper ion? Each copper ion's got to be +1 because there's 2 of them. And we know oxygen is 2-, oxide is 2-. So each of those coppers has to be +1, so you have +1 and +1 versus -2. Make it neutral overall. So that's going to be a copper 1 oxide. So you have to calculate the charge or find the charge on the metal before you can put that name in there with those parentheses. All right. Did anybody come up with a formula for cobalt-3 oxide? Okay. Yeah.
CO3.
So like this, COO3.
Yeah.
Is that right? Make it something different?
CO2.
CO. So you got CO2O3. So how can we figure this out? Let's go back to those ions and see how they balance out. This is just like building the compounds from last week. So we have.
It should be something like 5.
Okay, let's look at these ions. So if we see cobalt-3 oxide, all we see is that name. What are the 2 ions involved in this compound? What's one of them? Oxide, right? What's the charge on oxide? -2. Okay. And what's the other one? Cobalt-3, which is CO, and what's the charge? Got to be +3 because that's what that 3 tells us. The 3 right here says that's CO +3. So how do we make a compound from a 3+ and a 2-? Right, we need 2 of these and 3 of these. So now we have 6+ and 6- overall. 2 of these and 3 of those looks like that. So that's got to be the correct formula. COO3 wouldn't quite balance because you'd have 3 plus from the CO and then 6 minus from the 3 OO2 minuses. So you'd have a leftover -3 there. All right, what about that last one? Now nobody feels confident about it anymore. Back to the drawing board. That's all right. That's why we got to practice.
Is it lead, lead oxide?
Let's see. So lead 2 oxide. What do you think?
No.
Well, all right, so we know that we know it's lead, and we know it's oxide. We know it needs parentheses because lead is one of the kind of middle ones that doesn't always have the same charge. How do we determine what the charge is on lead? Yeah, it's +4 because each oxide is -2, and there's 2 of them, right? So the charge on the lead here is +4 to balance those out. Right. So rather than lead 2, this should be lead 4. Because it's 4 plus. The lead, let's look at the individual ions again. We've got lead 4 plus, and then we've got 2 oxygen, 2 minuses. All right. Okay. All right, so the trickiest parts of this, or the places where I see the most errors generally, are finding that number in the parentheses, realizing that's the charge, not a number of something, which means you have to figure that charge out from how many elements are there. The other common mistake is not understanding when or when not to use parentheses. So if I ask you to name something like BaCl2, what's the name of that one? Barium chloride. Would we use the parentheses for name?
No.
Why not?
But this one is 1, that one, that one is 2.
That's right. Barium always has the same charge. It's always +2. So if something always has the same charge, it's not appropriate to use the parentheses. In this case, it is +2, but we would not call this barium 2 chloride. So what do you think about this so far? Maybe? Should we make it a little trickier?
Mm-hmm.
Go on to the next little bit here. Throw one more wrinkle in, just for fun.
That's fun.
What?
Yeah.
Yeah? You having a good time? That's good.
That'd be better if you sin.
All right. It's not too bad, but people tend not to like this next part, so just fair warning. There is another class of ions that we have not talked about yet, but that you've probably heard of before because we used them in lab on last week, and that is the polyatomic ions. What do you think that means? Yeah, more than one, two or more ions. So far, we've only seen monoatomic ions. Chloride, sulfide, iodide, oxide. You just got one atom, and you make an ion of it. But there's this whole class of ions that are made from combining atoms together as well. And there's a few of them that are so common that I'm going to ask that you remember them and their charges. Some of them you probably already know because we've used them in lab, and you may have seen them around. Anybody know any that they can think of right now? They'll probably recognize them when I put them on here.
Nitrate.
Nitrate, that's one. In that kind of range. You know any other ones that kind of sound like that? Sulfate, that's another one. Phosphate, yep. So those kinds of things is what we're talking about now. Let's talk about what they are individually then. We'll start with nitrate. The formula for nitrate is NO3 minus 1. So it's a nitrogen and 3 oxygens, and the whole ion together has a charge of -1. Now, the bad news is there's no fun way of figuring that out like there was with the monoatomic ions. You can't find it on a periodic table or fill up some buckets and figure out what the charge is. You have to just know that nitrate is NO3 and it has an overall -1 charge. So this is the place, this is the section to make some flashcards or that kind of thing. Here are some more there's a list of a few of the most common ones that I'm going to put down here. And you need to know both their name, their formula, and the charge for all of these. These are also listed on Blackboard in the objectives for this chapter. So you can see exactly which ones you need to know. So we've got nitrate, carbonate, sulfate. Phosphate. PO4 3-. Bicarbonate, also known as hydrogen carbonate. That's the baking soda stuff. And one that's positive, ammonium, which is NH4 plus 1. Oh, and one more, sorry. Hydroxide, which is OH minus 1 or HO. I believe those are the only ones listed on Blackboard that you need to know. We can check if there's other ones. But other than knowing the names, the formulas, and the charges, these don't behave any differently in formulas and names than the other ions. So let's look at how we would construct a formula based on a name that uses some of these kinds of ions. For instance, copper 2 phosphate. You need to know a couple more bits of information to get this, but but now we do, so let's use that. What kind of ions are used? Well, first we need to know that phosphate is PO4 with a 3- charge. For now, since we just learned it, we can look at the chart and say, okay, phosphate is going to be PO4 3-. And what is the other ion here then? What's the positive ion?
Cu2 plus.
Right, Cu2 plus, because it's copper 2. So now we need to make a formula from copper 2 plus and phosphate 3- that is overall neutral. So how do we balance a 2 plus and a 3-? Remember? We just did it a couple times. What do we do? Well, we have to have a couple of, right, we have to have 3 of the 2 plus and 2 of the 3- to get them to balance. In this case, that's going to look like this. We have 3 of these and then 2 of these. Now, what does that look like when we actually build the formula? It's like this. Cu3 PO4 2. Because that PO4 is this polyatomic ion, this ion that stays together, we need those parentheses around it to show that that 2 goes to all of it, not just one or the other. So we can't just say PO4 2, because then it would look like 1P and 42 O's. Right? So we need those parentheses to say we want 2 of this whole thing. 2 of this whole thing. All right. So let's practice this. Try this one. All right, so you got 2 names. Sorry, I would have put more space, but I want to leave the names up here. So 2 names to formulas, and then 1 formula to name. Sodium bicarbonate, potassium carbonate, and then PbSO4 2. This time, when you think you've got some stuff written down, turn around and talk to the people around you and see how they match up or don't match up. If you have disagreements, try to defend what you did or maybe learn from what the other person did. All right, so what do you think? Just nothing? Complete wash? Meaning like,
Trying to figure it out.
okay. Let's look at these two. Let's look at this first one and kind of work through it together and see if we can figure it out. So first thing always to do is write down the ions. Just write them down so that we can see them and see how to balance out the charges. So what kind of ions did you write down for sodium and bicarbonate? Na is +1. And bicarbonate is HCO3 minus. We have to look that up on the table for now, but by next week you'll know them, right? So we've got Na plus and HCO3 minus. How do we balance those out to make a formula? That's it, right? We don't need to change anything. We got +1 and -1, so they balance. So our formula is just NaHCO3. +1 and -1, balance out. You're all good.
So we have to balance the charges, not like, I don't know, like I'm confused because that 3 next to the.
Right, but because that whole ion stays together, you think of it as one whole thing that's -1 altogether. Right. Sorry. All right, so how about the next one? Potassium carbonate. Right, so we're going to start with K +1 and CO3 -2. And that means we need 2 of these pluses to balance out that -2. So our formula is going to be 2CO3. Good. And then finally, PbSO4 2. Yeah, so this one's going to be lead and sulfate. Do we need parentheses here? We do, because lead can have a couple different charges. So what are we going to put in those parentheses? You heard it? Yep, I heard it a couple times. 4, 4, 4. Yeah, 4. How do we get 4? Right, SO4 is -2. So if we have 2 of those, as given by this little 2 down here, that means there's 2 of these for every 1 PB. If there's 2 2 minuses for every 1 PB, then that PB has to be 4 plus. Keep practicing that, you'll get it, and try to memorize those polyatomic ions as soon as you can. It'll be helpful. All right, the last piece then of our naming stuff is for the other type of compounds, and this is the easiest, so don't worry about this one as much. Molecular, also known as covalent, compounds. Now on Thursday, we're going to talk about what it means for a compound to be molecular, what a covalent bond is, what this all means chemically. For now, we're focused mostly on classifying things in this category so we can name them. Molecular compounds are always going to be all nonmetals. Now, that's not entirely true over chemistry. There's plenty of ways that metals can covalently bond and form molecules, but for our purposes of naming, we're going to say that if there's a metal involved, it's an ionic compound, and it gets all those rules that we've just been talking about. If there are no metals involved, we call it a molecular compound, and we use a different set of naming rules. So how do you know if something's a metal or non-metal? Remember from last week?
Last week.
Yeah, but what if you don't actually see it? What if that's true? But like, if I just gave you some elements, how could you tell if they were metals or not? Right, but what if you can't measure it? What?
The periodic table?
Yeah, how can you tell just from the periodic table? The groups, right? We can look at that stair step type thing, and we can say everything over on the right is a non-metal and everything over on the left is a metal. So for our purposes of naming. But you're right, all those other things you said about classifying metals are true. We just don't always have those tools, so we need some shortcuts. All right, so let's look at how we name something like this. Or something like this. These are types of compounds where it's not a metal and a non-metal, so all those previous rules don't apply. And in fact, between nonmetals, there's usually more possibilities of ways that these things can combine. For instance, there's N2O, there's NO2, there's N2O5. These are all compounds of nitrogen and oxygen. So we need some way of differentiating them. And the rule for naming nonmetals, or naming these types of compounds, is quite simple. You just say how many of each thing there is. There's no calculating charges or balancing things out or whatever. You just say how many there are with prefixes. The prefixes that we're going to use are, you may have heard these before, mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, and hexa for 6. We could keep going with all the standard prefixes, but we won't really see stuff more than 6 generally. So that said, let's look at this middle one first, N2O. We would call this dinitrogen monoxide. So technically it should be monooxide. Whoops, we usually drop that extra O. And we call that dinitrogen monoxide. So 2 nitrogens, 1 oxygen, dinitrogen monoxide. See, isn't that nice? Now here's the cautionary part from this. People tend to like this way of naming so much that they want to name all the ionic compounds using this way because it's easier. But that's not right. All right, so you can't go back up to this and say, oh, I don't know all of these polyatomic ion whatevers. I'm just going to call this sodium hydrogen carbon trioxide. Well, sorry, that doesn't work. So you still have to use all the rules for those kinds of compounds. But when you encounter compounds where there are no metals, then you use these compounds. So a couple rules to keep in mind. Usually, the second atom, whatever it is, becomes ide, just like in the ionic ones. So it's not dinitrogen monoxygen, it's dinitrogen monoxide. Another kind of unusual rule here, not unusual, but something that doesn't exactly fit, is you usually drop mono on the first atom. So this first one with 1 carbon and 2 sulfurs should technically be monocarbon disulfide. But we usually drop that one on the first atom. And so instead we just call this carbon disulfide. One way to remember that is to think of some ones that you know, like carbon dioxide. That's CO2, right? So it should be monocarbon dioxide, but we don't call it that. We call it carbon dioxide. That's a way that you can think about that. All right, that said, can you name these next two? And what would NO2 be? Right. Nitrogen dioxide. Now what about N2O5? Yeah, very good. Dinitrogen. Pentoxide. The nice thing about this is going backwards, going from the name to the formula is actually even easier. So if I give you the name phosphorus trichloride, what would that formula be? P? CO3, right. We don't have to do any balancing charges or anything. We just say PCl3, phosphorus trichloride. What about sulfur hexafluoride? How would you write that one? Yeah, SF6. Hexa-6, so sulfur hexafluoride is SF6. So this is certainly the easiest way of naming. The tricky thing is not using this where it's inappropriate. So for our last couple minutes here, let's put all of this together. And I'm just going to put up some random ones that could be in any of these categories. And you've got to figure out either a name or a formula. Use your resources for this one. So if you have your book or you have a periodic table or whatever, because I'm not going to go back up to some of those other tables, but you're welcome to use those resources. All right. So let's give this a try. All right, so you got 3 formulas and 2 names. Write the names from the formulas and the formulas from the names. If you're stuck or you got a question on something, let me know. Just let me know. All right, let's look at these. PDNO32. What's that? Right, this one's going to be Palladium 2 nitrate. Right, that one's in the middle, so it can have different charges. In this case, it's 2 plus because each nitrate is -1. What about P2O5? Yeah, this one's all nonmetals, so we can just use those prefixes and call it diphosphorus pentoxide. K2O. Right, this one is potassium oxide. No numbers because potassium is always +1. No dipotassium because it's a metal. This is not all nonmetals. Okay, what about rubidium fluoride? It's just going to be RBF. RB is +1 and F is -1. So you have +1, -1. They match right up to make 0. And nickel 2 carbonate. Nickel is Ni. And nickel 2 tells us that it is nickel 2 plus. Carbonate is CO3 2 minus. So you got 2 plus, 2 minus, they match right up. It's just NiCO3. That's why it's important to know the charges as well as the formulas for those polyatomic ions, because you need to know how many of each for each one. They have some different charges. It's going to take a little work, take a little practice, but by the time you get through the homework, hopefully you have a better handle on these. All right, we'll head up for lab. Make sure you've got appropriate shoes and stuff so that we can do the experiments. And we'll see you up there in about 15.
Yeah.